Welcome everyone. In the previous video, we have discussed briefly the model for the Schottky diode. Now we are going to complete this model by introducing the equivalent AC circuit model for the Schottky diode, and then we are going to discuss the different applications of such a Schottky diode based on the discussed model. Effectively, uh, we have discussed in the previous video the core of the Schottky diode. However, this core of Schottky diode is effectively connected with leads, and this leads has parasitic equivalent circuit. So actually, we have series parasitic inductance due to the leads connecting the Schottky diode. We have series resistance. We have a parasitic capacitance. In addition, we have the dynamic resistance of the Schottky diode, which we have discussed in the previous video, and we have the junction capacitance of the Schottky diode. And as we mentioned, the main advantage of the Schottky diode is that its junction capacitance is very small, so it can be used at higher frequency. So it is required to reduce the parasitic capacitance such that it does not affect the junction capacitance. So we say that the small signal approximation shows that the equivalent circuit of the diode will involve nonlinear resistance, and this nonlinear resistance is based on I saturation multiplied by e to the power alpha v minus 1, which we have discussed in the previous video. Uh, However, in practice, the AC characteristics of the diodes involve relative effects due to the structure and packaging of the diode. For example, the leads or the contacts of the diode package are modeled as series inductance and shunt capacitance. In addition, a series resistor Rs accounts for the contact and the current spreading resistance inside the packaging effect of the Schottky diode. So the complete equivalent AC circuit for the Schottky diode looks like this circuit. The junction capacitor and the junction resistance are bias dependent, which depend on the biasing voltage on the Schottky diode. And actually, they are representing the core of the Schottky diode. For typical values for Schottky diodes, for example, Schottky diode SMS 1546, its saturation current is around 3 multiplied by 10 to the power minus 7 ampere. The series resistance is 4 ohms. The junction capacitor is 0.38 picofarad. And the series inductance due to the packaging is around 1 nanohenry. And the parasitic capacitance due to the packaging is 0.07 picofarad. It is quite clear that the parasitic capacitance is much less than the junction capacitance, such that the dominant capacitance in this case is due to the junction, not due to the parasitic. If the dominant is the parasitic, we will not have the effect of the diode at all. Alright? For a better Schottky diode, we have smaller parasitic capacitance and smaller series inductance. However, for such Schottky diode, we have smaller saturation current and greater series resistance and a smaller junction capacitor. Smaller junction capacitor means that it can be used at higher frequency. And these are other two types of Schottky diodes. From point of view of frequency, maybe this is the best, but the junction capacitor here is nearly the same as the parasitic capacitance, and this is a great disadvantage in this case. Okay, so this is a figure of numbers for the equivalent AC circuit model for the Schottky diode. Now, we are interested in how this Schottky diode can be used as a rectifier. For a rectifier, we are assuming that the input signal consists of a DC from a DC component plus a small signal AC component. So the output, it would be the DC component plus an additional part proportional to the amplitude of the AC signal. Assuming that the DC signal is 0, so the output here, it would be proportional to the input signal, V0. This is a basic idea of the diode rectifier. Effectively, it is quite similar to the case of a rectifier at low frequency, but the situation here is different because the harmonic in this case is at higher frequency. So if the junction capacitor is slightly large, the harmonic will pass through the rectifier and the output will be mainly AC. So in this case, we are just rectifying the signal to obtain a DC component proportional to the input AC signal. To quantify the rectification of Schottky diode, we are going to use the equivalent model for the Schottky diode, the current as a function of the input voltage, where the input voltage, as I said, consists of a DC signal V0 plus a small signal AC with an amplitude small v. So the current as a function of the voltage, it was I0, which is the current due to V0, the DC current, plus V multiplied by delta I by delta V at V equal V0 plus half V squared delta squared I by delta V squared at V equal V0 and so on. And we said that the value of delta I by delta V at V0 is the transconductance or the conductance or the dynamic conductance of the diode. And the second derivative is GD dash, or the derivative of the dynamic conductance. So the output current I would be the output current due to the DC plus the amplitude of the AC signal V0 multiplied by the dynamic conductance of the diode multiplied by cosine omega naught t plus V0 squared over 2 V0 squared over 2 multiplied by GD dash multiplied by cosine squared omega naught t. We have here replace small v by V0 cosine omega naught t. Now let us simplify cosine squared omega naught t by half plus cosine half cosine 2 omega naught t. So in this case, we have a component which is frequency independent equal V0 squared over 2 multiplied by G dash D multiplied by half. So it would be V0 squared over 4G D dash. This will be frequency independent or DC. So it will be added to the DC component. So the complete output DC component in this case would be the DC current due to the DC voltage plus an additional DC due to the AC signal equals V0 squared over 4G dash D. This effectively is the rectified signal. In addition, we have V0 GD cosine omega naught t, And the second term from the cosine squared here, it would be half cosine 2 omega t. So half multiplied by v naught squared over 2, it would be v naught squared over 4 gd dash cosine 2 omega naught t. By using a low pass filter, we can take off the term cosine omega naught t and cosine 2 omega naught t. So we have only the DC component, which consists of two components. One component proportional to the input DC voltage, and the second component is proportional to the amplitude of the AC signal squared. That's what we are seeing here. I naught is the bias current, and V naught squared G D dash over 4 is the DC rectifier current. We are going to define current sensitivity and as beta I, and we are going to define this current sensitivity as the incremental change of the DC current with respect to the input AC signal. The incremental change of the DC current with respect to the input power. So the input power here is effectively proportional to V naught multiplied by GD, all of them V naught multiplied by GT, V naught squared, multiplied by GD over 2. So I think this V naught squared GD squared over 2. So delta IDC, which is V naught squared G dash D over 4 over V naught squared GD squared over 2. So we have 4 in the denominator, we have 2 in the denominator of the denominator. So we have 2 here. I think this should be GD squared. So the current sensitivity, it would be G dash D over 2G dash over GD squared, not GD. I think this should be GD. And this current sensitivity, it can be used to find out the voltage sensitivity or the open circuit voltage sensitivity. The open voltage sensitivity is defined as the current sensitivity multiplied by the dynamic resistance of the diode. So the open circuit voltage sensitivity, it would be beta I multiplied by the junction resistance Rg, and usually the range of the voltage sensitivity is between 400 to 1500 millivolt per milliwatt, because we are talking about delta V over delta B. So millivolt over milliwatt. And this open voltage sensitivity represents the voltage drop across the junction resistance when the diode is open circuit. So the diode is not connected to any load. If we are using the diode as a detector, the input signal, it would be modulated signal. So we have V naught cosine omega naught t multiplied by modulation signal, and the modulation signal, it would be 1 plus the modulation index multiplied by the frequency of the modulation signal, cosine omega m t. Omega m here is the modulation frequency, omega naught is the carrier frequency, and omega naught is much greater than omega m, such that omega naught at least 10 times omega m, and the modulation index m is greater than 0 and less than unit. This is simply amplitude modulation. So the input signal at the diode looks like this. It has carrier frequency plus two sidebands of the modulated signals. The expected output from the diode detector is that we have the amplitude of the modulation signal. So we will have a signal which is proportional to cosine omega mt, or which has a frequency fm, and its amplitude is proportional to the modulation index. To obtain the analysis of the diode detector, we are going to apply the model for the Schottky diode, and assuming that the input voltage is V naught plus V, where V here now is the modulated signal, V naught multiplied by 1 plus M cosine omega mt, cosine omega naught t. We are going to use this voltage and this equation. In this case, the output current of the diode would be the DC current I naught plus the small signal current small I. This small current or small signal current would be proportional to the dynamic conductance of the diode multiplied by V plus the first derivative of the dynamic conductance GD dash multiplied by V squared over 2. We are going to replace this small v by V naught multiplied by 1 plus M cosine omega mt cosine omega naught t. So the small signal current I, it would be V. V here is this voltage, V naught multiplied by GD multiplied by 1 plus M cosine omega mt cosine omega naught t. This is the first term. The second term, it would be the square of this value, so it would be V naught squared over 2 multiplied by G dash D multiplied by this bracket 1 plus M cosine omega mt to the power 2 multiplied by cosine squared omega naught t. Now we are going to simplify this square term, and also we are going to simplify this term. So we can say that, okay, the first term, it would be V naught GD multiplied by cosine omega naught t plus M cosine omega mt cosine omega naught t. Cosine, it can be represented as cosine the summation minus cosine the summation minus cosine the subtract of the two values over 2. So this would be M over 2 cosine omega naught plus omega mt plus M over 2 cosine omega naught minus omega mt. This actually the term M cosine omega mt cosine omega naught t. These two terms. Okay. Now the second term, we are going to take the square root at the beginning. Then we are going to multiply the square root. We are going to add the square of this bracket at the beginning, and then we are going to multiply cosine squared omega naught t by this square, and we are going to simplify the problem. So after simplifying the problem, it would look like this. Effectively, it is too long, but I'm sure that it is quite simple. It is some trigonometric relations. It is interesting here to note that this term contains many frequency components. We have DC component. We have a component proportional to the frequency of the modulated signal or the modulation signal. We have a component proportional to the frequency of the second harmonic of the modulation frequency. We have a component which has a frequency twice the carrier frequency, and we have a third order intermodulation frequencies, which are 2 omega naught plus omega m and 2 omega naught minus omega m. And once again, we have another component which has twice the carrier frequency. And also, we have components which has twice the summation of the carrier frequency and the modulation frequency, and twice the carrier frequency minus the modulation frequency. So we have a reach of components in this bracket. By taking this component together, we can represent the spectrum of the small signal current, in this case as follows. We have a DC component which is coming from this part, which has been already used as a rectifier. We have a component proportional to the modulation frequency omega m. We have a component which is proportional to the second harmonic of the modulation frequency, which is 2m. We have component proportional to the carrier frequency omega naught. We have component proportional to the carrier frequency plus the modulation frequency omega naught plus omega m. We have a component proportional to the carrier frequency minus the modulation frequency omega naught minus omega m. And then we have a component operating at twice the carrier frequency 2 omega naught. We have a component operating at 2 omega naught plus omega m. We have a component 2 omega naught minus omega m. We have a component twice omega naught plus 2 omega naught plus 2 omega m. 2 omega naught plus 2 omega m. We have a component 2 omega naught minus 2 omega m. So this is all the spectrum of the small signal of the diode detector. The relative amplitude of these components, the DC component here, is proportional to 1 plus m squared, the modulation index squared over 2. This term. This is multiplied by V naught squared over 4 multiplied by GD dash. So this is the DC component or the rectified signal. The frequency of the modulation signal or the component with the modulation frequency, it has a component proportional to 2m, 2 multiplied by the modulation index. And the component which is operating at twice or the second harmonic of the modulation signal has an amplitude m squared, the modulation index squared over 2. And as I said, the value of m is greater than 0 and less than unity. So m squared is much smaller than m. So it is expected that the second harmonic for the component with the modulation frequency, the second harmonic, it will be much less than the first harmonic of the modulation signal. Now by using a band pass filter, we can obtain the modulated signal, and from this we can use the diode as a detector. The remaining parts, the frequency component at twice the carrier frequency 2 omega naught is proportional to what? Here I have m squared over 2, and here I have 1. So 1 plus m squared over 2. The third order intermodulation, which is 2 omega naught plus or minus omega m, is proportional to m, and 2 omega naught plus or minus 2 omega m are proportional to m squared over 4, which is much smaller than m. So very briefly, the output spectrum of the Schottky diode if we have a DC component plus small signal AC component modulated with a modulation index M. Now, as I said, if we have a band pass filter around the modulation frequency, we can detect the required signal or the modulation signal. Effectively, to operate the diode as a detector, we are mainly operating in the second term. We are talking about the second term. So we are using what is called the square law behavior of the diode. In the square law behavior of the diode, the DC output or the modulated signal or the output modulated signal is proportional to the square of the input small signal. So the square of the input square, small signal is actually proportional to the input power of the small signal. So the output power or the output voltage of the Schottky diode when it is used as a detector or as a rectifier, the output voltage is proportional to the input power. And we call this is the square law region where the output voltage is proportional to the input power. As the input power is increased, this law will now follow up and we reach to saturation. So in this case, the output voltage is proportional to the input voltage or the square root of the input power. So we are using the Schottky diode as a rectifier or as a detector in the square law region where the output voltage of the diode is proportional to the input power of the small signal. The output voltage is proportional to the input power of the small signal. So we say that this square law behavior is usual operating condition for detector diode and also rectifier, but can be obtained only over restricted range of the input power. So it should be used before the saturation. If the input power is too large, the small signal condition will not apply, and the output becomes saturated and approach to be linear, and then it is constant. So I versus power characteristic, it would be I is proportional to the square root of the power. On the other hand, at very low signal, the output voltage, it would be below the noise level. So as we mentioned in the previous chapter, we have certain dynamic range for the diode as a detector, and this dynamic range is determined the minimum input power is such that the output voltage is greater than the noise level, and the maximum input power is such that it is below the saturation, and in the linear region of the detector, the output voltage is effectively proportional to the input power. So at very low signal level, the input signal will be lost in the noise floor of the device. Square law detector is usually or particularly important in many applications for detector. For example, for power level, for standing wave ratio meters. In standing wave ratio meter, we are using Schottky diode as a power detector to measure the power level at the different points, and from this power level we can calculate the standing wave ratio. Detectors can be DC biased to be operating at a certain point, or it can be used without DC biasing. Effectively, the advantage of DC biasing is that we can adjust the operating point, which provides the best sensitivity for the detector type. This is briefly how to use a Schottky diode as a detector. In the following video, we are going to discuss how to use this detector to build up an spectrum analyzer and what is the basic idea and what is the basic theory of the spectrum analysis. Okay,